So here we have Dave. Dave is from the Wellcome Sanger Institute. We've at Canonical, we've known these folks for quite some time, and yeah, they have a really cool use case for Ceph and S3 storage. So over to you, Dave.
Thank you very much. You haven't heard it yet. So yeah, my name's Dave Holland. I'm a Principal System Administrator in the High Performance Computing team at the Wellcome Sanger Institute. My team looks after compute clusters, Lustre, Ceph, OpenStack, the big toys like that. So I will talk briefly about what Sanger does and where Ceph fits in, and I'll talk about what went wrong and how we fixed it. So this is the Sanger Institute. We are based just outside Cambridge. The Institute was founded in 1992 as the UK's contribution to the Human Genome Project. That was a decade-long project to sequence the DNA of one human. It cost $3 billion, I think. So remember those numbers, 10 years, $3 billion. We'll come back to that in a second. You didn't think you'd get a biology lesson this morning, did you? So DNA sequencing in 30 seconds. The old-fashioned way is on the left. You jump around. You take your DNA, you smash it up, you add certain reagents to it, you shine a laser on it, diffuse it through a gel, and you see what glows. And from the colour of the glow, you can literally read off the A, C, G, and T. That's great, it doesn't go very fast. One of the new ways, on the right-hand side, is you unwind this helical molecule and you force it to go through a nanopore, a very small hole. You put a voltage across it and see what current comes out. And from that, you can infer whether it's A, C, G, or T. That's great, that goes much faster. So in some ways, some things haven't changed. That was 20 years ago. Looks like washing machines, it's actually DNA sequencers. They can produce 2 million bases, that's ACGT letters, in a day. So fast forward a bit, this is the sort of thing we're deploying now. They still look like washing machines, but look at the number at the bottom, 3 terabases, that's 3 trillion ACGTs per day. That number is incredible when I stand here and look back at it. Just to ram it home again, we had Moore's law mentioned in a previous talk. That's the white line there. You can see the y-axis is logarithmic. The cost of sequencing one human genome has plummeted. It's even beaten Moore's law. If you look at the left-hand end, that's slightly after the start of the Human Genome Project. So we're saying $100 million to sequence a genome. And then you come across to the right-hand end, we're below $1,000. We are nearly in mainstream kind of consumer technology. And we don't have washing machines anymore. Some of the sequencers are really small form factor. You can plug them into your laptop, you can plug them into your mobile phone, and these are producing not the big numbers of bases, but 20 gigabases, that's billion bases, I think, over 48 hours. We're still into producing vast amounts of data. And what scientists do with vast amounts of data, they want to keep it. And if that form factor looks familiar, here's another form factor that you might recognize as well. As I say, we are nearly into DNA sequencing becoming part of mainstream medicine. Everyone says it's really close, really close. The NHS is actually using DNA sequencing at birth for children with rare disorders or children of parents with rare disorders to try and capture things like this. Okay, enough about science. Let's talk about Ceph. About 7 years ago, our newish CTO said, not very keen on all this cloud stuff. Here, have some money. Go and build me a private cloud with some storage. Okay, we said we'll do that. And we didn't know what we were doing, to be completely honest. But what we ended up with was OpenStack on Ceph. So our first production system, after a few experiments and burnt fingers, was Supermicro, 9 machines, 3-way replication. This is all obvious to most of you. About a petabyte usable space. I get quite blasé when I talk about petabytes. I'll say only a petabyte. I know there are people out there with much bigger systems. We spent all the money we had, and we put some nice machines in, even 100 gigabit Ethernet, which is, it's not quite legacy these days, but it's getting there, but it still goes perfectly fast enough for us. What we found was, people loved it. We designed it to support OpenStack, the private cloud use case. So that's RBD. It's images, virtual machine images, volumes for disks that you attach to your virtual machines. And we thought, yeah, we'll turn S3 on because people might like it. They might use it a bit. Whoosh, it took off. People loved S3 as a data storage option because it's not a POSIX file system, but you can talk to it from anywhere. We took the possibly brave decision to expose our S3 service to the internet. So for dataset hosting, perfect. Collaborators can see it. You can upload it from anywhere. You can download it from anywhere. For website, in inverted commas, hosting, works great as well. It's not a web server, I keep telling people, but as soon as they figure out you can upload in index.html, they're all over it. And people have done some very, very creative things with JavaScript to make the lack of CGI and server-side stuff It's not quite an irrelevance, but people are doing real things. We've got a project which is called the Tree of Life project. They are trying to sequence every species in the United Kingdom. They put their QC data on this so that collaborators in the field can see what is the data that's coming out of the samples I collected. Does it look good? Does it look bad? And it's all sitting in an S3 bucket. It's perfect. Third use case I've put is data transfer. One of our clients, collaborators, is the government. I'll come on to that again in a little while. And as I said, the use absolutely took off. We thought we would have a little bit of S3 data. Turns out more than 3/4 of what we've got stored is actually Rados Gateway S3 use. So it grew. We keep growing. After expanding it, we're now up to about 4.5 petabytes usable. That's 51 servers. We started with 3 failure domains. We added a 4th. The overhead of managing individual servers starts to become slightly annoying at this scale, but it's okay. It's doable. When the S3 service really took off, we decided, yes, we need to add some separate Rados Gateway machines. So we added 6 dedicated machines for that, for HA proxy and as well for resilience. I should say the Sanger Institute is born out of academia. We don't really do SLAs, but on the flip side of that, people expect 100%. They just don't want to pay for 100%. So we have pretty good uptimes. We tend to aim for at least 99.9%, and we usually exceed that by some comfortable way. In the year since we've put it in, we've upgraded in place all the way through to Pacific. We are overdue an upgrade now. We're looking at getting to Reef by the end of the year. And I should say Ceph is generally hugely robust. We've done some awful things to it. Our users have done some awful things to it. Our data center and facilities team have done some terribly awful things to it. If I say that you can lose an entire failure domain, that's an entire cabinet, and it keeps going. Yeah, I'm really pleased with that. You don't see that from many other products on the market. So yeah, big thumbs up for Ceph. And there it is. I should say our data center is not actually built on a curve like that. That's the fisheye view. But wouldn't that be a cool data center to see? I know. Yeah. just don't tell the architects. So that is, it's a few years old, but that is our OpenStack and our Ceph intermixed to try and balance the power loading and the heat generation between the different workloads in the cabinets. So it's good, but occasionally it's really bad. Okay, in early 22, we started seeing crashes of OSDs. Now, we work with computers, everything crashes sometimes. What's troubleshooting 101 is you turn it off and on again. But these were more than just crashes. They came in waves, and you might get one OSD that would repeatedly crash, or you get a series that would crash, and it would, the users would notice that the latency went up because recovery was taking place. I'll be brutally honest, we didn't initially notice because systemd does a magic job of if something fails, it restarts it. If an OSD stops, it restarts it, and it restarts it, and it keeps restarting it until the damn thing stays up, please. One of my colleagues said, if an OSD restarts in the woods and no one's around to hear it, does it make a sound? Well, if you're not actually looking at the uptimes of your OSDs, and you come in on a Monday morning and everything's up, maybe you wouldn't know. We certainly didn't. Eventually things got so bad we did have a couple of more than 6-hour outages, and that focused our attention because I mentioned this was in 2022. You might remember there was a little germ called COVID doing the rounds then, and I mentioned that one of our collaborators was the government, and you might have seen in the news things like, oh, a new variant has been discovered. We were generating a large proportion of the data that was going into discovering those variants, so the government was really quite unhappy if they couldn't get their data in a hurry. My boss's boss's boss did not want to have to apologise to anyone from here. Yeah, moving swiftly on. We had a lot of help from Canonical support. They were really good. Backtraces initially pointed at garbage collection, corruption, bug, something like that. So we did some of the obvious stuff. We recreated the garbage collection pool. Didn't help, sadly. We tried disabling garbage collection. This is a good sign. Everything is suddenly back to stability, back to happiness. That's less good because our users are constantly churning the data. You can't be deleting stuff and not having it garbage collected. That usage will actually grow without bound if you don't turn the GC back on. So we spent a long time down the GC rabbit hole, and I've given the game away with the title of the talk. It wasn't actually GC at all. What happens is, when you delete a lot of things, and some of our users have workflows that create an awful lot of ephemeral objects or files, the object gets tagged for deletion, and later garbage collection comes along and goes and says, right, you, all gone. And that is quite a focused, quite an intense workload. And remembering that we are basically hard disks through and through, or were hard disks through and through, that could easily overwhelm an OSD. It stops talking to its peers. The peers say that OSD is dead. Ceph shoots it. Systemd says, hang on, wait a minute, I'm going to restart this, and we're into the avalanche. Particularly because once an OSD is out, recovery kicks in after a little while, and then you get more data movement because recovery is happening on top of the garbage collection workload. Everything is going to hell in a handcart, and I'm a sad sysadmin. What can we do about this? Well, it's easy, isn't it? We'll make it go faster. One of our jokes is, oh yeah, that's an easy problem to solve. Just insert credit card. So this was quite an easy one to sell because 8 2TB NVMe's is not going to break anybody's bank balance. We thought, okay, here's the plan. We'll stick some NVMe's in, and quite simply, we'll move the Valdos Gateway metadata off the hard disks onto something that goes faster. Great. It's a nice simple plan. You need to tell Ceph there's some NVMe's. You need to tell it, yeah, this data goes here. Maybe the final bit is not really profit, but in terms of happy users and happy sysadmins, that's where we want to be. So a few little nuts and bolts. This is about as technical as it gets. Some of you will have seen this already, but you tell Ceph, here's a new crush class for these devices. You tell Ceph this NVMe, number 123, is an NVMe device. You make an entirely new crush rule for laying out data on only these device classes, these NVMe's. We put it in where it's got default there, that's the default root. We are hanging all the data off the same root. And the failure domain is rack. Fine, so far so good. And the magic, as far as I'm concerned, the real magic happens in that last command. Tell Ceph, that pool, in this case, Valdos Gateway metadata, goes on that crush rule. And magically, without any service interruption, Ceph says, oh, it's in the wrong place, I'll move it. Okay, next. And I cannot praise the authors of Ceph enough. One single command can move an entire chunk of data in service without any disruption. I still think that's magic. So we tested it because we are sensible sysadmins and we don't just throw things into production, particularly on a Friday afternoon. We talked to Canonical Support, and again, they proved their usefulness. They verified our plan. We tested on a smaller cluster. We didn't actually test with the real NVMe's. That was hard disks only, so we declared them as fake NVMe's. It's just a label on the device class. We declared this hard disk is an NVMe. Let's go through the whole process. With those being hard disks, not real NVMe's, then some of the I/O workloads were a bit messy, so we tweaked some parameters to control the mayhem. And we tested, absolutely. It's transparent to users, it's transparent to Ceph clients, everything looks pretty good. Apart from a couple of little pitfalls. If you naively add OSDs to a cluster without telling Ceph anything about what's supposed to go on them, with the default replication, the default crush map, it says, oh, I need to replicate onto that, I need to put data onto here. We didn't really want the bulk data going onto the NVMe's. That was not the point. So there's an ordering here. You have to tell Ceph, these are NVMe's, this data is going here. You have to do that before you start adding devices. In particular, you need to tell it this data should only be on hard disks. When we did that, we found when we changed the crush rule for a pool from use any OSD to use any hard disk OSD, there was data movement. Not really expected. And actually, to be fair, not much data moved, only 0.15% of objects. Hang on, we're doing this at scale. We've got a billion objects. 0.15% of a billion is actually quite a large number that I want to care about. The technical details that Canonical explained to me, it's to do with the shadow root. When you change a crush map, you're changing where it fits into the hierarchy. If the numbers don't actually line up, then Ceph thinks data is moving. It's not really needing to move. They pointed us towards CERN's remapped script, and that did the job absolutely perfectly. We set no rebalance, moved the furniture, did the remap, unset, no rebalance, everything worked fine. Glorious victory. It did work fine in production, just as it worked in testing. You don't often hear that, but I'm pleased to say it did exactly what it was supposed to. No unexpected data movement, no interruption for service. As far as I was concerned as a sysadmin, I could turn garbage collection back on, have the deleted things absolutely deleted. And since then, Ceph has gone on to be, as it says there, reliable, robust, no complaints for where I'm sitting. So what do we take away from this? There are, I think, 5 key messages. System usage creep is a thing. Just because you've deployed a platform to do purpose A, the users will use it for purpose B and C and Z and theta, and who knows what they're going to do with it next week. We didn't intend for this platform to become mission critical or talked to by the government or anything like this. Things happen when you're not looking. If you can prepare for it, that's great. If not, you just have to dig yourself out of a hole. Second thing is to monitor the I/O rates. We didn't do that because initially we tried pointing all of Ceph with collect D at our metric system. It knocked the metric system over. There were simply too many metrics, too high a data rate, couldn't cope with it. So we selected things to monitor, and IO rates per OSD was not one of them. We had a blind spot and we got hit in it, simple as that. Third one is, it says don't be too quick to look for a bug. It's very easy to say something is going wrong, it must be the software that's at fault. Sometimes it is absolutely a bug. Sometimes it's an assumption or a design decision that you want to go back and revisit. Sometimes you need to take that step back and say, what is causing this? Having a test environment is invaluable. It's priceless. It's worth every money you spent on it and every arm wrestling match you had with your CTO to say, we need one of these, really, really, we do. Something that we do a lot in my team is we do sysadmin as DevOps. We keep configuration as code. We have CI tests on configuration. We run up test systems. We don't have the full CI on our Ceph, but we do take that mindset there. We don't deploy anything until it's tested. So test environment worth its weight in gold. And changing the crush map like this is only a little bit scary, particularly if you've got a test environment, but it brings a lot of power. You can say, in this case, we've ring-fenced these fast devices for Rados Gateway metadata. You could say, I've got, maybe my images need to go on fast storage because my users are standing up virtual machines all the time. They need the images to be really fast. You could say, maybe I've got a workload that needs a lot of object storage. You can ring-fence OSDs, pools, for particular purposes, and it's not really scary. I think that's something that we haven't really explored enough. It might be something that we look at in future for multi-tenancy, because at the moment we've got, as I say, this one big cluster with the exception of one tiny small cluster elsewhere. It might be something that we can leverage, if you'll pardon the jargon, for performance isolation and guarantees for particular projects. And that, I think, is it. I'm not even sure that was 10 minutes. I've got to look at the clock before the start. Nobody has waved at me. I'll take any questions. Sure, go ahead. Oh, sorry, there's a microphone coming.
Sorry. What version were you running when you
That is a good question. In 2022, we were on 2 before Pacific, Nautilus. Sure.
Thank you. Can you hear me? Okay, good. Right. I can't hear myself, so who knows? You mentioned that metrics and observability of Ceph platform was a real challenge for you. What have you done to address that since, so you don't get blindsided again?
We have not yet got a metric system that will take all the metrics that Ceph can provide, particularly if you turn it up to once a minute, which I think is collected default. We've got a new metric system on order, which is pure NVMe, so it can take that data rate. We are keeping much closer eye on things like OSD restarts, because an OSD restart should be a really unusual thing. It shouldn't happen for a reason. Typically, we see it these days. This cluster is, the oldest parts are 7 years old. Typically, these days we see it's because the hard disk is failing, and it's failing rather than failed. Smart has not yet kicked it out. Ceph has not seen enough errors to throw it out. But maybe the OSD has crashed because it got a read error.
Okay, I think it's a great story about the importance of observability and the fact that actually it's become a big data problem in its own right now. I have a second question.
Sure.
What's the worst thing your users ever did to your Ceph cluster?
Oh boy. I should have been prepared for this, because this is one of my standard interview questions. Tell me a disaster story. Thousands of millions of items in a single bucket, I think. And that might have been Nautilus, that might even have been Luminous, and it was a bit painful, yes. Okay.
Thank you very much, Dave.
I think there's one more.
Sorry.
Are you using dynamic resharding for buckets?
We are, yes. We turned that on. When did that come in? Was that Nautilus or Pacific? We turned it on when it came in. But it was a little bit hiccupy to start with. We had particularly the colleague who'd actually dealt with this problem left since then. I don't know if that was a causal relationship. We found that deleting objects would delete the head part, but not the tails. We went through a bit of a hoop, again with canonical support, trying to get rid of these leftover orphan pieces. But again, bucket sharding has mostly made that problem go away, as far as I can tell.
So you said that your current set of problems is a failing hard disk or like things like that, right, that you have to deal with. What's your experience with recovery, backfill in general, in terms of effect on client I/O performance?
In our case, for our cluster with our hardware, clients don't notice.
Excellent.
We notice because we have the dashboard and, oh, so many objects degraded, whatever. Users never notice.
Excellent to hear that. Okay, that's it.
Yeah, this is both for Dave and also our fellows from the core team. So is there any kind of tooling for simulate the impact of a change in the crash rules? Like based on this object base, there's going to be the amount of data moving. Yeah. Yeah.
We have it for the upmap runs, so that's an OSD map tool option, but not for the crush.
Okay. So you definitely have to use a test cluster, and that's the only
Exactly,
way
yeah.
to.
I think so. Yeah.
Okay. Thank you.
Hi. Sorry, this isn't really anything to do with your talk, but
That's
you
fine.
mentioned configuration management.
Yes.
And I'd just like you to say a few words about how you're doing that.
Okay. The one which is closest to my heart is probably for our LSF compute clusters. So we manage the entire LSF configuration. It's a job scheduler for batch compute. We manage the entire configuration in Ansible, and we have a CI/CD pipeline that stands up a new cluster when a change is made, deploys the configuration, puts jobs through, does obvious sanity tests like, does the job run, do the queues look like they ought to. Only when all those succeed does it deploy to production. But that is completely hands-off. Once you've pressed merge, once you've got approval and pressed merge on the change, it's hands-off. It goes through to production straight away. We're using GitLab for that. It's not an advert. Other systems are available, but it provides everything in one box, and we really like that functionality.
Up next, we have Jose.
Hi, everyone. My name is Jose Juan Palacios Perez. I've been working for IBM since 2007, and I joined the Ceph team earlier this year. I'm very excited. This is my very first Ceph talk. Hoping it's not the last. So, what I wanted to talk is my experiences in terms of gaining an empirical understanding of Crimson, in particular in terms of the CPU utilization. I'm not going to mention any of the metrics in this talk, but of course, the test involved measuring all the possible aspects. But in this case, I would like to focus only on the CPU utilization. Is right? Yes. So motivated by the early training earlier this year, we have several questions about Crimson. How does it compare with Classic? Can I saturate a single SSD with a single reactor? Questions like that. So that led this kind of plan to define some set of tests to measure performance with the main goal of identifying potential bottlenecks, contribute to the resolution of that, and of course to have a gaining in the understanding in terms of the source code in order to be able to contribute as well. So the contents is basically these points in which first measure, as is typical for performance testing, the I/O throughput in terms of the latency, and as I said, the CPU utilization, rather that the architecture of the new OSD Crimson is suitable for this, to fine-grained, so to speak, pin threads to CPU cores as opposed to Classic, in which Classic pretty much takes everything that is available. So in Crimson, it's quite interesting to measure what happens if I attach, can I attach a single reactor to a single CPU core, or define a set of CPUs, and how does the performance compares. And ultimately to have the response curves in which, as you know, the latency increases and the throughput doesn't. So you have the reference to know how to define a suitable queue depth, so you can create the same test and repeat it and have references according to your machine, but as well as a potential tool in which a customer could use and say, okay, I'm short on CPU cores, can I use a few of those for running my clients, and then cherry pick my reactors, things like that. So that could be kind of some of the outcomes. And in terms of testing, I think it's pretty much standard, starting with a minimal configuration involving a single OSD process. And in our case, in the kit that I had originally, I have only 2 sockets, 8 cores per socket. Not going to use hyper-threading, so dedicated a single socket for the client for FIO. I mean, everything in the same box, and the other socket dedicate 4 cores for the I/O reactors and 4 cores for the alien threads, and then examine the impact. And I use it along all these tests, the flexible I/O exercises, which is pretty much standard for Linux, and compare it with a single running instance of FIO versus 8 at the most. And I had a single SSD, so at most I used a single OSD, but also tested up to 8 RBD images, 10 gigabytes each. So I'm obtaining the performance curve, as I mentioned, to have the saturation points and provide a summary report and define what the next steps will be. Just a brief mention, is not a very powerful kit, but it's good enough for the purposes of having, as I said, just a feeling what could be done with this. In particular, in terms of the figures that the SSD, it would be possible for a single reactor to saturate a single SSD. Spoiler alert, it is. So things like that. So in the way in which I run it, the cluster was only for in developer mode. So these are the standard flags that I used, and the only backend that I used was the Bluestore. So as I said, this is just a summary of the configuration that I already mentioned. Segregate manually the alien threads in 4 cores. I didn't use the hyper-threading. And this might be a point of discussion. It was arbitrary for me to say, in the team, 10 milliseconds would be enough to have this, to look at the performance curves and decide which are the I/O depths that could be used and define them in that. I use other experiments, for example, the I/O depth of 128, which decided which was the more convenient that switched within 10 milliseconds. This is just a summary of many tests that we did. On the right-hand side, you have the client, the FIO. On the left-hand side, you have the Crimson OSD process. The order of the CPU appears which is the one that occupies the most. And on the bottom, you have the threads for the OSD process, and correspondingly the threads for the clients. So looking at these figures, of course, this was a very high I/O depth of 64. Looking at these figures, we could start asking questions like, for example, what happened if we segregate this into a single core? Or what happened if for the client we do something similar, because this doesn't seem to be very high in CPU utilization. So things like that, and that led us to, for each of the 4 typical workloads, that is 4K random write, 4K random read, and a variety for the sequential workloads. I tried with 64K, 128, and 256, if I remember correctly. So for all of this, I computed this, pushing the system to saturation. As we can see, the 10 milliseconds will be around here. So for that, we can select which was the most appropriate I/O depth for, in this case, for the random write I/O depth of 16, which is a parameter of the FIO, and with 4 jobs. For the sequential workloads, we used only a single job, so that was a single parameter because of the way in which FIO does the I lost my train of thought. The way in which it deals with sequential workloads. This is a quick summary of that gives us the ballpark figure, so to speak, in terms of the workloads and the parameters that will be needed in order to achieve that throughput. All this within 10 milliseconds. as I mentioned earlier. In the multiple FIO, it was only a maximum of 8 FIO running processes, each one exercising its own RBD image. It was not a kind of a contention simulation in that case. So that was kind of a good exercise. The results of the outcomes of these experiments provide us the queue depth for reference in FIO, so we can have the predetermined values for each workload, and then it can be used for terms of repeatability. The same experiment will have the similar results, as well as providing the profiling data in terms of the top measurements, as well as perf, in order to have flame graphs and use it to compare. If we do a code change, we will be quickly able to compare what was the performance impact. Also, as a result, all that I did previously was before I was aware of CBT, the Ceph benchmark tool. So all I did was in batch, a few lines of batch exercising in the node. But these ideas have been, I submitted a PR for extending the Python code in the librd FIO for CBT. So it will support this methodology. It will be able to recreate these similar results or in different machines, so to speak. I mean, using the corresponding parameters in order to reach saturation in the machine and then have it for future execution. And also, as a result, I've been collaborated on a tracker to provide recommended deployment values for Crimson, as well as weekly updates on the Crimson performance column. Oh, sorry, that's me. Thank you very much.
Thank you very much, Jose. Any questions?
So you've seen me already, but I just want to say that this is really nice to see that the Crimson project has matured so much that we are able to see some endeavors to see how it reacts in terms of differently to CPU behavior and stuff, and it's mature and stable enough to really survive the test that Jose was presenting to us today. So that's really cool, and I wanted to thank you for saturating the OSD and to present us to us. That's it.
Thank you, Matan.
Any more questions?
I'm not sure if you mentioned that, but can you just repeat, how did you simulate the workloads?
There is a Linux exerciser, which is called FIO, and that is a kind of a standard benchmark for running I/O. In particular, in this case, was for RBD, for the block images. So FIO, you can define either from the command line all the parameters, block size, queue depth, things like that, or you can define in a file with a certain format all these configuration parameters. So I wrote some lines in bash to call FIO, which was exercising the underlying block storage. And yeah, essentially it's like a loop starting from the low number of queue depth and low number of jobs, increasing it, pushing it, comparing the performance, the throughput, the latency, and providing the flame graphs, sorry, the screws, which show the saturation point, so to speak.
Thank you.
So I saw that you have just distinct sizes for the I/O size. Did you test mixed I/O sizes in concurrence? Not yet.
No.
Okay.
It was 4K for random, 64 for sequential. I didn't test the mix at this point, no.
Okay.
So how hard was it to deploy the cluster, the Crimson Ceph cluster?
No, it was pretty much kind of straightforward with the bstart script. I only played with a single parameter in those days because we are not extended for more. It was the number of cores, and then manually with TaskSec, segregate the alien threats in separate cores. But it was pretty much smoothly. A couple of weeks, I managed to hit a segmentation fault, but that's another story.
I want to hear more about the segmentation fault. Next question. Yeah, next question.
Yeah, hey Jose, I'm putting the hat of the UX here. So what's more or less the amount of settings that you had to tweak? And also that's also for Madan. Is there any plans to have like profiles or auto-tuner for this?
Not yet, but with FIO, since it allows you to define predefined files that describe the workload, you can have like a library of workloads. So the plan is that we can reuse it in CVT. And CVT, you can define a plan in a YAML file. So in particular, we're extending the YAML to support workloads. So you can define, I'm started in this range, or push the machine until you have, say, 10 milliseconds, 20 milliseconds, or something that you are interested in your machine. Probably that will apply for my particular kit. I mean, it's a bit 5 years old, but it's still working. So yeah, things like that.
And how many settings did you have to tweak?
Well, to be honest, mainly focus on two: the number of jobs and the queue depth. Well, IO depth that is called in NFIO.
Thank you.
No problem.
All right. Thank you very much,
Thank you.
Jose.